We are going to close the subject of set cardinality by reviewing some results here. First of all, there is no infinite set that is smaller than set of natural numbers. So the set of natural numbers, as I said, is the baseline. It is the smallest possible infinite set. It's the countable infinite set. So essentially what we say is there is no infinite set A such that the cardinality is strictly less than Aleph null. So Aleph null is the first step of infinity, let's say. It's countably infinite, and whatever is above it, it's not countable. But we do not have a level of infinity below it. It's the first level of infinity. If set A is infinite, then there exists a set B such that B is a subset of A and B is countably infinite. Now here we are saying that set A is infinite, but we are not specifying whether it is countable or not. So essentially, given any infinite set, we can find a subset of this set that is countably infinite. This one we have already shown. For any positive integer, the Cartesian product of natural numbers with itself this many times, or in fact the set of integers, is still countable. Okay, and next one, for any set A, the cardinality of set A is strictly less than the cardinality of its power set. Remember, the power set is the set of all subsets of a set. So the power set of A has all subsets of set A, and this is a quite important result, and this demonstrates that there are infinitely many levels of infinity. Why is that so? Remember, because let's say a set of natural numbers has cardinality Aleph null, set of reals is greater than this set in cardinality, but there are sets even greater than set of reals because, well, its power set of reals from this result we know to be greater than the cardinality of reals. And whatever this set is, if you take its power set once again, this is still a set, and its cardinality will be even bigger than this one. Okay, so by defining power sets, you can define new levels of infinity, essentially. So it goes indefinitely. Therefore, there is an infinite level of infinites. Next result, if A and B are countable sets, then their union is also countable. Now, countable here is a more general concept than countably infinite. Countable also includes finite. Okay, so if a set is finite, it's a countable set. If a set is, well, countably infinite, it's also, of course, countable, but it can also be finite. If two sets are countable, then their union is also countable. And seeing this is not that difficult. Of course, assuming that they are disjoint sets, and getting rid of this assumption is not that difficult, so I'm just going to skip over it. The first case, let's assume A and B are both finite. In this case, obviously, the union is also finite, so it is countable, simple. Case number two, let's say set A is a finite set, but set B is countably infinite. In this case, in the union, just, well, I'm just going to give you an enumeration, let's say, of the elements. So put the finite number of elements of set A first, and then list all the elements of B. And you can do that because you know that B is countable, so there really exists such a list. So at the beginning of the list, just append these finite elements. So you still have a list. that is properly defined. So the union is countably infinite. And finally, both of them are countably infinite sets. So you just interleave them. You have a list of elements of set A because it's countable, and you also have a list of elements of B because that set is also countable. So you just take one from one at a time. A1, B1, A2, B2, A3, B3, etc. This will give you a proper listing, which means the elements of the union of A and B can be listed properly, which means it's a countable set. And finally, something I have touched upon earlier, if you remember when we talked about proofs, continuum hypothesis, sometimes denoted with CH, and the statement is there is no set whose cardinality is strictly between Aleph null and continuum C. No, what this is saying is the immediately next level of infinity that is above countably infinite is the set of reals. This is the claim with this hypothesis. But the interesting thing about the continuum hypothesis is that it is independent from the Zermelo-Fraenkel set theory. So what does it mean? Being independent means we can neither prove nor disprove it in that axiomatic system. And Zermelo-Fraenkel set theory is essentially the modern and widely accepted set theory, an axiomatic set theory. Um, and we also have what is called the axiom of choice, sometimes appended to this set theory to make it, instead of ZF, to make it ZFC. So this is Zermelo-Fraenkel, and sometimes if you add the axiom of choice, it becomes ZFC. Okay, so this statement, well, it was, well, some mathematicians believed it to be true, some believed it to be false, but nobody could find a proof. Of course, in 1940, Gödel showed that the continuum hypothesis cannot be disproved from ZFC. So we cannot disprove it. Look, this doesn't mean it's true. It just means we cannot disprove it using the axioms of the set theory. And then, more than 20 years later, Paul Cohen, he proved that continuum hypothesis cannot be proven from ZFC. Okay, so what does this mean? This statement is undecidable. We can neither prove nor disprove it under ZFC set theory. So it's interesting in the sense that it provides us with a very famous undecidable statement and indicating the limits of mathematics in a general sense.